this is speed of a wave. We're going to call that the Greek letter nu, which looks suspiciously like a V, but is different, equal to lambda f, where this is now the frequency in hertz. Right? We're talking cycles per second, not radians per second, which is equal to lambda omega divided by 2 pi. Okay? So again, the speed of the wave is given by the wavelength times the frequency in hertz, which then we just convert into angular frequency. And then, ta-da, this is this thing over here. So this is velocity squared. So the velocity of a wave traveling down a string or a rope is given by the tension on that rope divided by the density, right? A more dense or more heavy string or rope or chain or whatever is going to have slower waves, right, as this thing gets higher. And the more tension we put on something, the quicker those waves travel, right? Because those tension forces are higher, and that's what causes the wave to move. Okay. So then we're going to rewrite this, just plugging in this, rewrite the wave, that wave equation we had, plugging in this nu, and we have that the second derivative of displacement with respect to time is equal to the velocity of the wave squared times the second derivative of the displacement with respect to time, and this is the general wave equation. So I want to point out that this is not an equation that just has to do with ropes or strings like this. It's called the general wave equation because it's completely general. Anything that acts like a wave obeys this equation, right? The strings and ropes, water waves, sound waves. Quantum mechanics teaches us that all matter is fundamentally made up of waves. So actually everything in the universe, in a sense, obeys this equation, right? Not this, the quantum mechanical wave equation is slightly different, but it's similar in principle, right? We get this equation from analyzing that string and that rope and the tension forces, etc. But this works for basically anything, which is why it's called the general wave equation, okay? And it's very simple and elegant. You may take a moment to appreciate its mathematical beauty if you wish. But one important characteristic of the wave equation is what's called linearity. Okay, what does that mean? Okay, let's just algebraically rearrange this. So I've done nothing but algebraically rearrange this, right? I've factored out the derivatives in the velocity after bringing this guy over to the other side, right? So we have some series of derivatives and a multiplication by a constant acting on this d, giving us 0, okay? So what linearity means is that this d only appears once and it doesn't have any exponents. Okay? The rest of the equation can be thought of as kind of a mathematical operation on this function that returns 0. Okay? Now, I wrote down that that solution, that's sine kx minus omega t, right? But my choice of k, essentially my choice of lambda, and my choice of omega, any choice of those two things is a solution to this equation. It just describes a different type of wave. okay, a wave with a different shape, right? But say I have, I solve this equation for 1 omega and 1 t, and I get d1. And I get d1. I can solve it again and get some solution d2 with some different omega, right? Or some different t, and I can go on and on like that. I can have many, many multiple solutions, and then here's the trick, is that I can make a new solution, some d prime, by adding any two other solutions. So because of the linearity of this, because there's no exponent here, and this d only appears once, I can take any two solutions to this equation, add or subtract them, right? I could add or subtract them times some constant also, and then this now I can guarantee is also a solution in the wave equation, right? If we plug this d prime into here, this would separate out into two equations, each of which would be equal to 0. Okay. So this is an extremely important and general point. It tells us that if we have a set of solutions to the wave equation, we can write any function that's a solution to that equation by adding up those other solutions, right? So any two solutions added together are guaranteed to also be a solution. And once you get to some higher level classes, you'll see that this linearity, this ability to separate out solutions like this, leads to what's called Fourier transforms and signal analysis. So if any of you are planning to be electric engineers, that this is an extraordinarily important fact in signal processing and electronics and stuff like that, right? And in fact, not to go off on too much of a tangent, because this really isn't too important for us, other than we can do this, but just to give you some flavor, if you've ever listened to music while watching a little visualization in your, whatever you use for your music player, right? You see some shape, and that shape kind of like moves up and down and has weird spikes and stuff like that. That's what's called the Fourier transform of the music you're listening to. It's the frequency space, right? Each solution of this equation represents a different frequency of a wave, and I just told you I can add up any number of waves, and that gives me another correct solution. So if I'm listening to some music, that music is made up of however many different frequencies added together up linearly like this. So when you look at that visualization, really what that is if all of these d's are the functions of different omegas, right, and on and on and on, that visualization is just telling you how much of each solution you get in the music, right? So if something was all one frequency, I would just have this term. If it was all another frequency, I would just have this term. If it was a half and half combination of those two frequencies, I'd have these two added together, right? So why does this matter for us in looking at our string? Well, I wrote down that solution before. All right, let me back up a little bit. Okay, so now we're going to talk specifically about music. So imagine I have a guitar string, and I reach down and this is the guitar string stuck between 2 points, and I reach down and I pluck it, right, and boom, whatever sound it makes. So I pluck this string, and I can model me plucking that string, right? Say I pluck that string in the center. I can then model this as a wave moving this way and a wave moving that way. So when I pick up this string, that's like doing this with the rope, except when I let go, that wave is going to travel in both directions because I'm doing it from the middle of the string, right, instead of from the end. So this means that if I want to know the wave equation for plucking the string, so P for pluck, I've been called pluck so many times in my life that it's almost my name. Yeah, this is a P for plick. How about that? Okay. So that the wave equation for the pluck string is going to be equal to a wave traveling to the right plus a wave traveling to the left. So we can now find the solution of this pluck string by adding up two known solutions of a right moving wave and a left moving wave. So, so what I have is, I have this I wrote down those solutions earlier. So now that is going to be amplitude sine 2 pi over lambda x minus omega t plus a sine 2 pi over lambda x plus omega t. Okay. So the difference between the right and left moving one is whether I have a plus or a minus sign here, right? So if I define positive frequency, right, as a wave moving this way, a negative frequency is moving in the other direction. So when we flip this negative sign, that just means the wave is moving this way instead of that way. Okay, and then we add them up, and then it's the joint solution of this plus string where the waves are moving in both directions. So now we need a trig identity. Sine alpha plus minus beta is equal to sine alpha cosine beta plus minus cosine alpha sine beta. Okay. And then we use this trig identity on this dp, and we get dxt equal to 2a sine 2 pi lambda x times cosine omega t. Okay, so something really interesting just happened. Is after using this trig identity on this equation, actually I don't need to, hold on. This equation separates out into two parts. I've got this part here. This is only space, right? There's no t in this equation, right? There's just, or this half of the equation, there's just x. We could think of this as the amplitude, right? So that amplitude as a function of x. This part is only time. So we can look at just the amplitude, right? What is the shape of that guitar string after we pluck it, okay? And of course it's going to vibrate, but that vibration is fairly simple. It's just a cosine omega t. At each point along the guitar string, that thing's moving up and down, right, up to some amplitude, but it's all doing it at the same frequency. Okay? When I pluck a guitar string, I get an oscillation that's totally regular in frequency. Okay? Which is why when I pluck that guitar string, those vibrations produce a pure tone. I have one frequency in here, and each part of the string along, or each point of the string along the string vibrates with that same frequency. Right? If this didn't turn out to be the case, each point of the string would be producing a different frequency, but because this factors out, I have one pure tone being produced by plucking that string. And if I have multiple strings, all of different lengths or masses, that's going to alter that frequency, right? Like we saw when we looked at the constants for the solution to our wave equation, right? That different frequency is what produces, for each string, is what produces the tones that we hear when we play a stringed instrument. And so this isn't just guitar strings, right? Any kind of instrument works by some form of vibration, because vibrations of the air is what sound is, right? So we can apply this same idea to a wind instrument or anything else, right? Or drum, etc., etc. So hopefully that was that was a little interesting, learning about how we get to music being made just from examining our simple Newton's law type stuff with a couple of algebraic and calculus tricks. Okay, so, all right, that's all I wanted to talk about, and we're ending just about on the correct time. Like I said, no more lectures. On Friday, I'll send around a practice final for you all to do. I have not decided quite yet exactly how the final will work, but I will hopefully get that figured out before I send you the email that says that this is uploaded. Okay. So I would like to say it's been a pleasure to have you in class. The first 2/3 of the semester was a pleasure until I stopped seeing all of you and just spent all my time speaking to my phone, which is not as fun. But hopefully, you know, by next semester, everything's calmed down a little bit. Okay. Well, that's all I really have to say, and I'll see you when I see you. All the best.